Key concepts. Equations and graphs of a polynomial function. The graph of a polynomial function can be sketched using the x-intercepts, the degree of the function, and the sign of the leading coefficient. The x-intercepts of the graph of a polynomial function are the roots of the corresponding polynomial equations when the polynomial is in factor form, when zeros can be easily determined from the factors. When a factor is repeated n times, the corresponding zero has order of n.
The graph of a polynomial function can be sketched using the x-intercepts, the degree of the function, and the sign of the leading coefficient. The x-intercepts of the graph of a polynomial function are the roots of the corresponding polynomial equation. When a polynomial is in factored form, the zeros can be easily determined from the factors. When a factor is represented n times, their corresponding zero has order n. Analysis. We're going to analyze a polynomial function fx equals negative x to the bracket of x minus 1 to the power of 2 bracket x plus 3 bracket to the power of 3. The degree is the product of all factors that will give you a multiple of x to the power of 6. The function is a degree 6. Leading coefficient is the product of all x coefficients is negative 1 multiply 1 multiply 1 equals negative 1. N behavior is the n degree polynomial with a negative leading coefficient extending from quadrant 3 to quadrant 4. Zeros are 3, order 3, 0, and 1, order 2. The y-intercept is 0, bracket 0 minus 1, bracket to the power of 2, bracket 0 plus 3, bracket 3 to the power of equals 0. Polynomial functions of a degree 2 or greater can be drawn using a series of smooth connected curves, as in this example below. In polynomial functions, in this example is the function fx equals 3x to the power of 5 minus x to the power of 2 plus 4x minus 1, a polynomial function. Fx is a polynomial function. It has degree 5, a leading coefficient of 3, and a constant term of negative 1. Note that there are no x to the power of 3 and x to the power of 4 terms. This is because the coefficient on these terms, a3 and a4, are both 0. This example is the function fx equals 3x to the power of 1/2, a polynomial function. Fx is not a polynomial function, but a radical function. The exponent in the polynomial function are always whole numbers. When we want to specify specific values, we say that as x approaches some value, fx approaches some other value. This is denoted mathematically by as x approaches a, fx approaches b, where both a and b are either constant or infinity.
Example 4. State the n behavior of the polynomial function below. As we can see, the function extends from quadrant 3 to quadrant 1. As x is negative infinity, fx becomes negative. As x becomes positive infinity, fx becomes positive as well. Power functions. A polynomial function with a degree 4 is called a quartic function. The quartic function fx equals to x to the power of 4 is similar in shape to the quadratic function we all know, gx equals to the x to the power of 2. And it's illustrated below. Power functions continued. All power functions with an even degree have the following characteristics. The x and the fx intercept is the origin. The DOMA is in negative infinity / positive infinity. The range is 0, infinity, if a is bigger than 0, and negative 0 if a is less. The end behavior is from quadrant 2 to quadrant 1. As x is negative, fx is positive, and as x is positive, fx is positive as well, if a is bigger than 0. If a is less than 0, the end behavior is from quadrant 3 to quadrant 4. As x is negative, fx is negative, and as x is positive infinity, fx is negative infinity. The graph is also symmetric in the fx axis. Describe the characteristics of a possible power function that could describe the graph below. The end behavior is from quadrant 2 to quadrant 4, so the power function has an odd degree. Given the end behavior, the leading coefficient of the function is negative. The graph is symmetric about the origin, further confirming the odd degree. The function is flatter near the origin than the graph of dx equals to x cubed, implying one of the two possible scenarios. The degree is 5 or greater, there is a vertical compression.
The parameters a, k, d, and c in the polynomial function of the form y equals a at k at x minus d to the power of n plus c, where n is a non-negative integer, corresponds to the following transformations. A corresponds to the vertical stretch of compression, and if at less than 0, our reflection in the x-axis. K corresponds to the horizontal stretch of compression, and if k is less than 0, our reflection in the y-axis. D corresponds to horizontal translation to the left or right. C corresponds to the vertical transition up or down.
We have obtained the parameters in order to graph a polynomial function of the form y equals to akx minus b to the power of n plus c. This function can be sketched by applying transformations to the graph of y equals to x to the power of n, where n can be any real number. The transformations represented by a and k must be applied before the transformations represented by c and d. In this example, we want to describe the transformations applied to y equals to x to the power of 3 to obtain the graph y equals to negative 1 over 2 x plus 1 to the power of 3 minus 2. This function is the image of fx equals to x to the power of 3 under the transformations defined by negative 1 over 2 x plus 1 minus 2. Since a is negative 1 over 2, the function is compressed vertically by 1 over 2 and is reflected in the x-axis. Since d equals to negative 1 and k is equal to negative 2, the function is then translated to 1 unit to the left and 2 units down.
Okay, now we're going to be talking about AROC and IROC, average rate of change and instantaneous rate of change. Now, on this curve, on the graph, we take 2 points, A and B, and the slope between the 2 points is called a chord, and the slope of the chord AB is the AROC between points A and B. Now, let's take another point on the curve, C. Now, if we take the slope between these 2 points, that is the chord of AC. And the chord of AC is the A-rock between points A and C. And now let's take another point on the curve D. And the slope between A and D is the chord of AD. And the chord of AD is the A-rock between points A and D. And if you notice, as we get closer points to A, the chord becomes closer to the... Cut it. Okay, now we're going to be talking about A-rock and I-rock. Instantaneous rate of... Cut that.
Go.
Okay, now we're going to be talking about A-rock and I-rock. Average rate of change and instantaneous rate of change. Now, we have a curve on this graph. Now, let's take a point on the graph A. And if we draw a tangent at A, the slope of the tangent is the I-rock at A. Now, let's take another point on the curve B. And the slope of the line between the 2 points A and B, the slope is called the chord. And in this case, it's the chord of AB. And the chord of AB is the A-rock between points A and B. Let's take another point, C. Now, the slope between these 2 points is the chord of AC, which is the A-rock between points A and C. And if we take another point, D, the slope of the chord AD is the A-rock between points AD. And if you notice, if we get closer points to A, the slope of the chord will become similar to the I-rock at A as we get points closer to A.
Okay, now let's take a look at example 1. The graph represents the amount of money in a bank account over a period of 8 months. Determine the A-rock of the amount of money in the account for the given intervals, month 0 to month 4. Now, we are given the points 0, 400, and 4, 1,000. Then we use the equation for A-rock, which is equal to the change in amount over change in time. And in this case, it's 1,000 minus 400 divided by 4 minus 0, which is equal to 150. So the amount of money in the account is increasing by $150 per month. Okay, now let's move on to the next part. Month 4 to month 6. So, we are given the points for 1,000 and 1000. Now we just have to use the equation for a rock, like before, which is equal to 1000 minus 1000 divided by 6 minus 4. 1000 minus 1000, 0. 6 minus 4, 2. So it is 0. Now, since the A rock is 0, no change occurs. So the amount of money remains the same in the account. Alright, now let's take a look at example 2.
Okay, the table shows the population P of a bacterial culture T minutes after an antibacterial spray is applied. Determine the AROC of the number of bacteria over the entire time period. So, the point in the start is 0,800, and the point at the end is 540. We will use these points to find the AROC for the entire time period. Now, AROC is equal to the change in population over the change in time, which is 540 minus 800 divided by 5 minus 0, which is equal to minus 52. During the entire 5-minute period, the number of bacteria decreases on average by 52 per minute. And because of this minus sign here, this is how we know that it decreases. Okay, now let's move on to the next part, which says, estimate the IROC in 4 minutes. To estimate the instantaneous rate of change in 4 minutes, meaning at this time only, we take the point at minute 4, which is 4,681, and a point at the next minute, or the minute before it. In this case, let's take the point at minute 5, which is 540. Now, let's solve for the IROC using these points. IROC is equal to 681 minus 736 divided by 4 over 3, which is equal to minus 55. So, in the 4th minute, the number of bacteria decreases by 55 per minute. And again, this minus sign represents that it decreases.
Done. Now, let me start a little joke. Now it's time for functions to stop caring about its ex. And it's time for it to find someone else. Cut. How's it going, students? Today, I'm going to be teaching. Start again.
Yep.
Count down.
3, 2, 1.
Now, we are tired of finding the X for math. And we should just tell math that it's time to go find someone else. Now, the equation for transformations is y equals
Alright. It's alright.
cut it.